Hi there, I'm Daryl Percy, and I'm going to give a brief presentation here on real process modeling in heavy industry like oil and gas, mining, pharmaceutical, pulp and paper, these sorts of industries, and how the control systems are implemented there. And we're going to be talking about how you need to model the plant and why you need to do that and how it's done with bump testing and how that's different from what's taught in academia. So here we have our plant, and you might wonder, why do we need to model it? Well, the thing is that to get your control to respond the way you want it, most of the control design techniques that are taught are in the Laplace domain, and then you have, for example, internal model control, pole placement, lambda tuning, Q design. There's a lot of different techniques in the Laplace domain, but all of them have one thing in common. You need a model of your process, the plant, the thing you're trying to control, in the Laplace domain also. So how is that done? Well, if you look in a lot of textbooks, you're going to find them telling you to use first principles of science, physics, chemistry to model the dynamics of whatever system you're trying to control. Here you see an example. This is a pretty famous example where you're controlling a pendulum with an upside down pendulum on a cart, and you see these differential equations. Well, you know, if you have a simple system like this, I'm sure everybody looking at this op amp and this here, this LRC circuit, everybody's modeled the transfer function of these sorts of systems, and you understand them well, and it's easy to do. And even you can get a pretty good transfer function of something like this. This is a common emitter, and you see here this big, long, intimidating looking transfer function. I actually built that PCB that you see in the picture there, and it behaves according to the transfer function, you know, within about 10%, and the error can pretty much be attributed to tolerances in the parts. And you can even take that common emitter and cascade it with a bunch of other similar smaller circuits, and one after the other, and their transfer functions likewise cascade and multiply into each other, and you can get from the input to the output and get a huge transfer function of this much bigger circuit. Here, for example, is an op amp. So these are just examples of applications where transfer functions really are used in design, and they really do work. So I'm not saying that they don't work or that they're fake or something like that. But those systems were fairly easy to model because they were well understood and they can be cascaded like that. But if you look at a system like this, it's got a lot more going on. The process is a lot more complex, and it just seems that most companies aren't going to be willing to pay for PhD chemists to come in and model the process, and probably their modeling wouldn't even be that good because it's just too complicated. Well, if you're not going to model it analytically, how are you going to do it? Well, it's done with bump testing. So you put here, as you can see, a step output is put on the output of the controller, and then what's going to happen? You're going to record the output of the controller and the output of the system, and notice that there's no feedback here. This is what's called open loop. So you're in manual control, meaning you're controlling the output of the controller and you're telling it, put out this step and we're going to see what happens on the output. And this is also in the time domain, not to be confused with some Laplace domain analysis. These are all going to be graphs like we are used to in the time domain. When you do this, it reveals three key facts about your plant, your process that you're trying to find. The first is the process gain. The second is your process dead time. And the third is your process time constant. We're going to go into detail about what these things are and how they're obtained. The dead time, the gain, and the time constant, these are all for the process, and they give you a nice estimated model. Well, once you have those measurements, there are well-known empirical formulas that have been come up with over time by various experts, and you can basically just plug that data into these formulas and come up with the sorts of values you need to tune your PID controller. A point that should be made here is that we've shown a step output on the controller, but it's not always a step. Pulse and double pulse are also used. Pulse would be more like an impulse, more like a Dirac delta type short burst, and that has the benefit over the step that it doesn't move the process as much. The process doesn't move as far from its equilibrium point. If you don't want to disturb the process too much, it's advantageous. Double pulse is even better because you put one upward pulse, one positive pulse, and then one negative pulse. And the net result of those is that the process ends up pretty much back where it started, so it's even less destructive. And also there are advanced methods using noise and complex patterns, and those are actually used quite a bit in distributed control systems that are automatically looking in the data for these sorts of events so that they can use it to analyze the process and find out what's going on in the process. Another fact about the bumps, or another kind of important point, is that you don't want to have huge bumps here on the controller output. You don't want to go from 0 to 100 on your controller output because that's very jarring to the plant. You don't want to damage the plant. You want to have just small bumps, a few percent in difference in the output. Whatever your output happens to be, you bump it up by a few percent and see what the result is. And that tends to be a lot easier on the plant. Well, now we're going to look at an example of a real open loop test that's being done on an air compressor. This is courtesy of a company called BTC Instrumentation. They have hundreds of videos on YouTube showing real control applications from industry. And you're going to be able to actually hear the air compressor responding to the step that they put on their controller output. And you can actually hear the instructor talking to his apprentice there about what they're going to do with this data. And it corresponds exactly to what we're going to be talking about in this presentation. Now, another reality of testing is that in real big plants, you might have to do a closed loop bump test, which is different. You can see that the feedback is hooked up here. This might come about because you simply aren't allowed by policy or due to safety. You're not allowed to disconnect the feedback here just so because you want to perform some open loop tests. They might say, no way, it's too risky here, it's too expensive, we can't afford to have the system go down like that. So you have to do the testing here while the system is still in automatic. This tends to be safer than open loop. It's safer for the people, it's safer for the process. It's not as damaging to the process because the feedback brings the process back to its equilibrium point. And also you get a faster return to normal operations. You're supposed to be typically in closed loop, and you stay in closed loop, so you don't need to hook that back up or account for any changes in the process or wait for it to cool down or anything like that. An important consideration when you're doing open or closed loop testing is that you want your test to be free from noise or disturbances. You want the pure response of the plant to your step input that you're putting either on the controller or here on the set point. You don't want this input disturbance. This could be like something shaking your plant, shaking your pipe. You don't want this output disturbance either. This could be something shaking. And here's some high frequency noise. You don't want any of these things interfering with your results. The latest research in this area is model predictive control. This is the latest technology that you're going to be finding in these big, expensive systems. You don't have to have gigantic, huge, expensive distributed control systems in order to do this type of analysis. There are smaller software packages that can do it for you. You can do it in MATLAB. There's a special tool, system identification toolbox. You can do time domain and frequency domain data, and it can analyze and kind of guess what type of model. You can propose that it might be a fourth order model. I don't know how you would decide that, and I've talked to control PhDs, and they also say, you don't really have a way of knowing whether it's second order or fifth order. You don't know, but you can take a guess and say it's second order and see what MATLAB comes up with and see how well it matches your data. Here are some other companies. This is Control Station. I'm going to be showing you a lot of good graphs and a lot of good information that comes from the founder of this. He's a professor down at University of Connecticut, and I think he's been quite successful with this software Control Station, and he has a lot of insight into how control is really done. And here's another company. I believe this is a South African company here, Techmation. They make some hardware that you can bring on site called ProTuner. We're going to take a look at how that works. It's quite insightful. Here's an example of how ProTuner 32 does its job. Here you see the data. This is real data coming from the output of a plant, and here's your controller output in your open loop test. And look what they do here. You have the time domain data, and how do you find the transfer function? Well, here's the transfer function of the process is just the output of the process over the input of the process in the Laplace domain. And what is the input to the process? It's the controller output in this case. And you have that time domain data. So what do? You just take the Laplace and look, there you are. You're taking the Laplace transform. And now there's another little question about this part, a little mathematical detail, which is quite a serious detail. And how they get data to infinity is, as you can see, it's in steady state here. So you just pad a huge amount of data at the end of this data here. You just pad it with the steady state value to simulate a value going to infinity. So you can do a summation. Of course, now the computer would be doing this with summation, and then you get right there's your result. There's your transfer function. I've seen some examples of the type of polynomials that result from, and they're huge. I mean, it was like a seventh order polynomial, which, that's something that would only be done by computer simulation, and according to the technician, according to the people who use it, it's pretty accurate in a lot of cases. So what does this mean? Well, that's actually good news for us as humans, because it means that INC technicians and engineers are needed to go out into the field and perform tests and do the tuning. So how do you analyze this data? What are these? Now we're going to go into some more detail about these things, dead time and gain and time constant of the process and what they mean. So let's say you do your open loop test out in the field, and you want to know how do you analyze this? What is the time constant? It's the time here. You look here. This is it here. This is the process time constant. It's the time it takes for the process. This is the output of your process variable, or the ultimate thing you're trying to measure. It's the time it takes. Here's the total response of it. It goes from here to here, and here's the amount of that total change. The time constant of the process is the time it takes to drop or change by 63% from this value to this. If 63% of its total change, that's the time constant. And where that number comes from, that's this number is derived from a first order differential equation that's kind of assumed to represent this process, and we're going to go into more detail about that. Now we're going to talk about the dead time, and here it is here. This time between here and here is the dead time. Now look, the controller, you put your step on the controller, and look here, the process variable that the controller is controlling doesn't respond right away. It takes a while for it to start responding. So this time here, where it's kind of not doing anything, it's not responding very well, that's your dead time. Now, that's really up to your judgment. You might say the dead time ended here because you see it going down just slightly. You might say it ended here because you see it going down slightly here. That's really up to you. It's a matter of judgment. And finally, we're going to look at the process gain. What is the process gain? It's the ratio of the controller output, the percentage increase in the controller output, to the percentage change in the process variable, the thing you're ultimately trying to control. Now, basically, it's how much you get out for how much you put in on the controller. It's this ratio here, and you can see here that there's a bump from 38% to 42% of total controller output, so you got a 3% bump there, and you can see that it affects the your process variable. It decreases by 1.6 degrees, so then you get this ratio here, and that's your process gain. Now this is a pretty good example of how you want to use small bumps on your controller output. You don't go from 0 to 100. You're going from 38% of total output to 42% of maximum output. You're not going from 0 to 100. That would be way too damaging to your process. This process happens to be a heat exchanger. Who knows what the precipitous drop would be here in your temperature if you jammed this all the way up from 0 to 100. Who knows what would happen to your equipment if you changed the temperature that quickly. So you don't want to do that. Well, now we have our time constant, our process dead time, and our process gain. So what are we going to do with it? Well, what we're working on here is an assumed model. When we started this analysis, we assumed that the process we were looking at follows the dynamics that are described by this equation here. It's a first order differential equation, as you can see. But now the question I have is, what are we going to do with this? I mean, okay, great, we have an equation and we assumed it, alright, but now what? Well, it's not a problem because we've already obtained our time constant, our dead time, and our process gain. And a lot of work has gone into these parameters because a lot of processes in industry seem to follow the first order plus dead time model plus time delay model. And so a lot of work has gone into it over the years, and here's one example of a set of formulas that's come about. Well, you'll recognize here's the from a PID controller, here's your proportional gain, your integral time, and your derivative time. These are the parameters for a series form PID controller. It's very common. And you can look here, look at the formulas. Well, it's these same quantities that we've already measured. So in other words, all you have to do is measure these and plug them into these formulas. And as long as it's a first order plus dead time model, really, or pretty close to it, then pretty much these are going to be good parameters for you to plug into your PID controller. Oh, how easy is that? Now you might wonder what's the theoretical basis behind these. Well, some sets of formulas are purely empirical. This was derived in the 1980s from internal model control, which is a Laplace domain method. So these do have their roots in Laplace domain analysis. Internal model control is certainly that. But for the point of view of practitioners, you don't really need to know that. What you really want to know is how to tune your PID controller, and it's pretty easy to do, as you can see. And the question you might ask is, does it really work? Well, yes, it has been in major industry for a long time. Yes, it does work as long as your process really comes close to a first order plus time delay model. And you might wonder, okay, once I get these proportional gain and derivative time and integral time, how do I actually tune them? How do I actually do the tuning? Well, this is an example of a programmable logic controller. It's very common in industry. The Allen Bradley PLC5 is a very popular one. Allen Bradley is a trusted brand in not only in airports, in sawmills, just all over the place. You're going to find these, and there's a lot of professionals out there who have a lot of good advice on how to use them and program them. Well, how do you actually implement your PID in here? Well, look at this. This is the GUI for the Windows programming environment for the PLC5, and there you see right there, you've got your proportional gain, your derivative time, and your integral time. You just calculate them according to the formulas to the left and plug them in there, and there you're good to go. That's pretty easy. That's about as easy as engineering gets. Now, I go into a lot more detail as to how these things really work and why in my other video, and I'm going to put a link to that below. So if you're interested, you can check it out. Thank you.